Hi, in this session we'll discuss the concept of distance in a graph. Okay, so what do you mean by the function distance in a graph? So basically the distance is defined between two vertices. So the distance between any two vertices is the length of the shortest path between them. So that is the definition. Okay, so suppose we'll denote the distance symbol by d. We'll denote the distance by the symbol d. So basically distance between any two vertices, maybe v comma w, will be basically the length of the shortest path between them. Okay, for example, if you look at this graph. Okay, so please look at this graph. So you can see two vertices are here. Suppose v1 and v2. Suppose we need to find the distance between this v1 and v2. I need to find the distance between v1 and v2. So what I'll be doing is that I'll be enumerating some paths between v1 and v2. Okay, so I can go from v1 to v2 through this edge A and this edge E. So one path is I can go from v1 to v2 through A. I can reach this v1, then I'll take E, then I'll reach v2. So that is one way. So I'll use these two edges. So basically it is A and E. That is the one path between them. Another path between v1 and v2 is I can use this edge B. I can go through F to reach v2. So another path is basically B comma F. I'm just writing only the edges here. And another path is B C. So I can go through B, I can go through C, and then I can go through E. So it is another edges B, C, E. So this is another path between them. Okay, and we can find more paths. Suppose if I want to bring a longer path, I can go from B, I can reach G, I can go to I can go to J, then I can reach V2. So therefore B, G, I, J. So you can see that there are paths of many lengths here. So basically the distance between V1 and V2 will be the shortest of these paths, and you can see the shortest of these paths are basically of length 2. There are two such paths, A comma E and B comma F. So the distance between V1 and V2 is actually 2. So I hope it is clear what do we mean by distance between any two vertices. It is basically the shortest path between any two vertices. Okay, so it is the determination of distance is actually easier in the case of a tree, because in other graphs you can see, like in this graph you had many paths and you have to enumerate those paths and then find the minimum distance. But in a tree you know that there exists exactly one path between two vertices. So the determination of the distance is very easy in the case of tree, because you can see that only one path will exist between any two vertices. So that will be the length of that path will be the distance. Okay, for example, in this is a tree. I suppose I need to find the distance between D and A. What is it? This is the only path between them. It is basically 2. Okay, it's D and A. Suppose I need to find the distance between C and B. It is basically 1. Okay, distance between C and A, that is also basically, what's the value of distance between C and A? It is basically I need to come to B and then I come to A. So basically distance between C and A is actually 2. Okay, because in a tree exactly there exists only one path between any two pair of vertices, hence the determination of distance is much easier in the case of tree. So, okay, so that's it. So we will so now what will be say is that why is this function the function of calling the shortest path? Okay, so basically this is a function on two variables, right? So distance in a graph basically it gives the shortest which basically gives the shortest length between shortest path between any two pair of vertices. It basically gives the number of edges in the shortest path between any two pair of vertices. That is what distance does. Okay, why is it called distance? We have already heard distance in many other concepts there. So why are we calling it exactly as a distance in a graph? Because the reason is because it has all the properties of the familiar distance function we have earlier studied in our lower classes. Okay, so distance between two objects, distance between two points, distance between two towns. So it has all the properties of that distance function. Okay, so that is why it is called distance. So I am going to write the common properties of a distance function. So I am going to write the common properties of a distance function which you have studied in other maybe other fields. Okay, so basically what are the properties of the distance function? The first property of distance function is it is always positive, it is always greater. So distance between any two objects is always positive. Okay, that's the first property. That's called a non-negative property. Okay, so the first property of a distance function, if a function is to be a distance function, the first property is that it should be greater than or equal to 0. Okay, the distance between two objects cannot be negative. Okay, and moreover, it will be 0 if and only if both the objects are just the same. So distance between two objects will be 0 if and only if both the objects are exactly so if and only if x is equal to y. For example, if you are considering points in a plane, okay, you know that suppose this is a point here, this is a point here, the distance between them will be the length of the line segment joining them. Okay, you know that the distance between A and B will be the length of the line segment joining them, and you know that this length of the line segment is always positive, so distance is always a positive function, and this length will be 0 if and only if both the points are just the same. Okay, so that is the property, one property of distance, that is called non-negativity condition of a distance. Okay, so if you look at our graph, the way we have defined distance in graph is basically the length of the shortest path. Since it's the length of the shortest path, it will be the number of edges, so it will always be positive. Okay, so non-negative condition is actually true in the case of distance which we have defined in graphs also, because it always gives you the length of the shortest path, which is always a positive number, and the length of the shortest path will be 0 if and only if I am starting at a vertex and ending at that vertex itself, that is all if and only if both the vertices are just the same. So in a graph, basically distance between two vertices will be 0 if and only if the shortest path between them have length 0, that means both the vertices are just the same. Okay, so non-negativity condition is true in the case of graphs. Okay, the second property of a distance function, the general distance function, is that for example the distance between a and b and the distance between b and a is just the same. So basically the distance from going from a to b and distance from b going from b to a is just the same. So that property is distance of x y will be equal to distance of y comma x. Okay, that is true in the case of graphs also. Why? In the same graph, if you look at the distance of v1 and v2, it is 2, and if you look at the distance of v2 and v1, it is also 2. So the shortest path which you take from reaching v1 and v2, you can reverse that path, you can change the order of that edges, you can reverse all those edges to get the shortest path from v2 to v1 also. Okay, so basically distance of v1, distance between v1 and v2 is same as distance between v2 and v1. This is called the symmetric condition, which you have studied already in relations. Okay, this is called similar to a symmetric condition. Okay, it's called a symmetric condition. Okay, so first condition non-negativity, and second one is symmetric condition, and the third condition is very important. Okay, so that is basically a geometrical idea. Okay, suppose I need to go from a point, this is generally I'm talking, suppose I need to find the distance between a point a and b. So then distance is basically length of the line segment joining a and b. Okay, and suppose there is a point C. Okay, so I need to find the distance between A and B going through C. I must go through C. So what will I do? First I will go from A to C, then I will go from C to B. So that is the distance of that is the way of reaching A and B through C. Okay, so one way is directly you can reach from A to B. Another way is that we require to reach A to reach B through C. Okay, suppose we start from A, we need to go through C to reach B. So that is the condition there. Now can you talk of these two ways, which will be longer? Okay, will the direct distance between A and B longer, or the distance between A then C and B, which will be longer? It is obvious that this distance will be longer, right? Okay, so this property is called triangular inequality. So this is formally we can write it like this: distance of AB is always less than or equal to the distance from A to C, distance of A to C plus the distance of C to B. Okay, so this property, so the direct distance is always less than or equal to a distance through a fixed point. Okay, so this is called the triangular inequality, and it will be an equality if and only if basically C is lying between A and B. Okay, suppose my C is lying here, so that distance will be equal then. Okay, because then distance of AC plus distance of CB will be same as distance of AB. That is why it is less than or equal to conditions given to that. Okay, so always the direct distance is always less than or equal to distance through a fixed point. So that is the third property of a general distance function, that is distance of x comma y is always less than or equal to distance of x comma z plus distance of z comma y. Okay, so this is called the triangle inequality, because you can see a triangle here. Okay, so basically this is the property of triangles also. You know that in a triangle the length of one side is always less than or equal to sum of the length of two other sides. So that is how the name comes, triangle inequality. Okay, so these three properties is the basically a general distance function. A general distance function is called by the name metric. Okay, so a metric, okay, the metric basically means a general distance function has always these three properties. What are these three properties? First one, it is the distance function, or the metric would be non-negative, and it will be equal if and only if the 2 points are just the same. And similarly the symmetric property, distance between any two objects will be same if you go from x to y or y to x also. Okay, and the third property is triangle inequality, that is the distance between x comma y, and we say it will be always less than or equal to distance from x to z, and distance between x comma y will always be less than or equal to distance to a fixed point. Okay, that property is also there. Okay. Okay, so the distance between any two vertices will have this property also. So okay, so the triangle inequality also is there. So the triangle inequality will also be true in the case of graphs, because you know that if suppose I need to go from v1 to v2, okay, then that distance is always less than or equal to the distance taken by going through this vertex. Okay, so less than or equal to. Okay, suppose I need to, I am requiring that the path should go through this way, this vertex. Okay, so the direct distance between V1 and V2 will always be less than or equal to distance. Suppose this is the vertex V3. So the direct distance between V1 and V2 will always be less than or equal to distance taken through V3 as an intermediate point. Suppose the distance between V1 and V3 is actually 2, the distance between V3 and V2 is 1. So if you take a fixed vertex and I am require the path to go through this vertex, that path will always be greater than or equal to the original distance between V1 and V2. Okay, so in that graph also, the way we have defined distance, the shortest path will always be less than or equal to the path through a fixed vertex. Okay, because we are actually taking the shortest path, so it can be less than or equal to any other path between these two vertices. So the shortest path between any two vertices will always be less than or equal to the path between any a fixed vertex. Okay, so if I require that we should reach V2 through V3, then that path will definitely be longer. So or if you require that it should reach V2 through V4, it can be longer or equal also, because we can find three paths through V4. We can go from V1 to V4, then we can reach V2, that path has length 2, then I can go from V1 to V4, then this path, then I can come there, that has a path length. So basically in this case the length is just the same. Okay, if you require the shortest path through V4, the length of that path will be basically same. Okay, but if you require the path to go through V3, the length of that path will be greater. Okay, so in a graph the distance between any two vertices is always greater than or less than or equal to distance through a fixed vertex. Okay, so the triangle inequality is true in the case of graphs also. Okay, so we can always say that the distance function which you have defined in graphs satisfies all these three properties. One is non-negativity, second is symmetric property, and third one is triangle inequality. Or we will say that the distance function is a metric. So distance in the graph is a metric. Okay, so this theorem is there and you can go through it. So this is also a very important theorem. Distance between any two vertices in a graph is a metric. We have to just now discuss it. It's very basic thing. First you have to know what is a metric. Metric has three properties. It is non-negative, symmetric, and triangle inequality, and then we have to establish that all these properties are true in the case of graphs also. Okay, and moving forward, now we will be discussing about basically trees only. So we will only be considering trees now. Okay, so in a trees, what do we mean by, so there are many vertices, or what do we mean by eccentricity of a vertex? Okay, what do we mean by eccentricity of a vertex? Okay, so idea is very simple. You take a vertex here. Suppose I take a vertex here. Okay, so suppose I am taking a vertex D, then I am writing the distance of D from all other vertices. So distance of D to D to B is 1, distance of D to A is 2, distance of D to C is again 2. Okay, so the maximum of all these distances is called the eccentricity of D. So it is called eccentricity of D. That is actually, in this case, it is 2. Okay, similarly, suppose I am taking the vertex B. So let us try to find the eccentricity of B. So the maximum distance, let us write the distance of B from all other vertices. So distance to A is 1, distance to D is 1, distance of C is 1. Okay, so the maximum distance is here 1. So eccentricity of B is 1. And similarly, if you look at A here, let us try, can you find the eccentricity? What are they? Distance to D, distance to B will be actually 1 will be there, right? And distance to D will be 2. Okay, so distance to B will be 1, distance to D will be 2, and distance to C will be 2. So the maximum distance will be actually 2. Okay, I hope it is clear. Okay, and similarly, can you find the eccentricity of C? That will also be 2. And I want you to understand one more observation. In the tree, you can see that the maximum distance is always obtained at a pendant vertex, at an end vertex. You can always see that the maximum distance for any vertex is obtained at a pendant vertex. Okay, so basically the maximum distance from D will be at a pendant vertex A. So maximum distance for D occurred at 2, 2. Both of them occurred at a pendant vertex A and C. The maximum distance of B was always occurring at a pendant vertex which was D, because it was D also there, A also there, C also there, because only at the end you will be getting, at some endpoint you will be getting a maximum distance. So the maximum distance will be occurring only at an endpoint. Okay, because if it is an interior, suppose the maximum distance is, suppose here is a edge also is there, suppose this is also there, suppose the maximum distance is occurring at D, it is not possible, because again I can bring a longer path to E there. So the maximum distance from any vertex, suppose B, always occurs at a pendant vertex or an end vertex. So that's a simple observation. Okay, so this is clear. And again, we can look at this graph. We have actually written the eccentricities of all the vertices here. Can you see that? For example, what is the eccentricity of this vertex? First, the distance of this vertex to this edge was, this vertex was 1, and this vertex was 1 again, and here it is again 1, and to these two end vertices is basically 2 and 2. So the maximum is 2. Okay, so similarly, what is the eccentricity of this vertex? The distance to this vertex is actually 1, distance to this vertex is actually 2, the distance to this vertex is actually again 2, and distance to other two vertices is actually 3 and 3. So then, so eccentricity is actually 3. Okay, so you can see that the maximum distance occurs for that vertex also at an endpoint. Does not mean it occurs at all the endpoints, because at this endpoint distance is 2, but the maximum distance from this vertex always occurs at some endpoint there, and that endpoint was, there were two such endpoints here and here. Okay, so distance from this endpoint, this vertex to this endpoint was 3, and distance from this vertex to this endpoint was again 3. And similarly for this vertex also, the maximum occurred at some endpoint. Okay, so distance from this to these two endpoints were 1. Okay, but these two vertices 3 and 3, or these, not 3, these two vertices were actually 2. Okay, so the maximum distance for this vertex occurs at some endpoints. Okay, so this is the idea here. So in this graph we have labeled all the eccentricities. We have already marked all the eccentricities in this graph here. We have already marked all the eccentricities in this graph here, and the vertex with a minimum eccentricity is called a center. Okay, the vertex with minimum eccentricity is called the center of a graph. Okay, there can be many such vertices. Okay, for example, in this graph there are two vertices with minimum center 2, minimum eccentricity, that is 2. So that's, there are two centers here. In this graph, there is in this graph, if you write down all the eccentricities, if you in this graph here, if you write down all the eccentricities, you can see that what will be the center here, which will be the center here. Okay, the eccentricities of all other vertices in this graph will be 2, 2 and 2. Only this one it will have eccentricity 1, so this will be, so in a graph there can be one center, two center, and many centers. In a cycle, you can, if you look at a cycle, you can just check it out, all the vertices will be a center in a cycle. In a cycle like this, basically, if it's a cycle like this, so some vertex here, some vertex here, some vertex here, so all the vertices in effect will be center, if you can check it out. Okay, so basically in a graph there can be many centers. So what is the center? It's a center is basically a vertex with minimum eccentricity. So such a vertex is called the center of the graph. Okay, so I hope it is clear what do we mean by distance. Okay, what do we mean by eccentricity, and what do we mean by center? Okay, so now okay, now we'll prove an important result for trees. That is, a tree will always have either one or two centers. Okay, a tree will always have either one or two centers. So before we try to understand the proof, we'll try to illustrate the proof first of all. We'll use by means of some examples. Okay, so the result is that a tree has either one or two centers, and some other graphs there can be no center or many centers, etc. So a tree will have one or two centers. So that's fixed for a tree. Okay, so let us look at how is it so. Okay, so if you look at this graph, this is a tree here. So we'll make some observations before we move forward. As I always told you, always the maximum distance from any vertex occurs at a pendant vertex. Okay, for example, if you look at this vertex here, what is the eccentricity of that vertex? So it is not written here. What will it be? It will be here the distance would be 1 to all these vertices. Here it will be 1, again 2, 3, again 4. So basically 1, 2, 3, 4, 5. So eccentricity of this vertex is actually 5 here. You can check it out. The distance of this vertex from all these four vertices are actually 1. Distance of this vertex from this vertex is actually 1. This vertex is 2. This vertex is again 2. This vertex is again 3. Okay, distance of this vertex from this one is 2. This one is 3. The distance is 4, and this one is actually 5. So the maximum distance is actually 5. So you can see that the maximum distance at any vertex occurs at the when the other vertex is a endpoint. Okay, and what is the center of this graph? Can you check out the center of this graph? If you look at this graph, can you find out the center here? The center is this one's marked here. It's the center. Okay, now what we are going to do is that, now of course you know that the pendant vertices cannot be centers. Why is it so? Because the center is a vertex which with minimum eccentricity. So if you have a pendant, if your center is an end vertex, what will happen? Generally, if your center is an end vertex, what will happen? Again, if you take at the other end, if you suppose this is one end vertex here. If you look at the other end point, you will be getting a bigger, longer path there. So your eccentricity will be much greater than an eccentricity at some interior vertex. Okay, so the center cannot be a end vertex, because if you take it as an end vertex, what will happen is that its length will be much greater than an interior vertex. Okay, but this is not the case in the case of simple graphs. Some simple graphs you can see that the center can be endpoints. For example, if you might take a simple tree as a consisting of a single point, basically this will be its center. There's only one point there, so this will be the center. Okay, and if you're taking another tree, for example, this is a tree with two vertices. Both these vertices would be the center because there are no other vertices. So they are endpoints as well, and they are also the centers. Okay, so except these three vertices, if you take another vertex, suppose this is another tree, these two cannot be the end vertices. This two cannot be the centers because, of course, the eccentricity of this vertex will be actually 2, the eccentricity of this vertex will be 1, and the eccentricity of this vertex will be 2. So apart from these two vertices, for every other tree, okay, the center cannot be an endpoint. Okay, because if it's an endpoint, you can always find you can always see that the distance from that endpoint to some other endpoint will be longer than a distance between any one vertex being an interior point. So basically the centers cannot be the end vertices, okay, generally. Okay, so this is the graph here, and we have marked the eccentricities here. Okay, and you can also see that the maximum distance occurs at a pendant vertex. Okay, and suppose the next stage what I am going to do is that I am going to delete all these pendant vertices. Suppose I am going to delete all this. Suppose I am going to delete all this, but I am going to delete all of them. So I'll delete them, I'll delete them, and I'll delete them. So I'll be getting a resultant tree will be there. Okay, now what can you say about the resultant tree? What will happen to their eccentricities? Okay, you can see that the eccentricities of all the vertices will be uniformly reduced by 1. Why is it so? Because the maximum distance of any vertex occur when the other one was an endpoint. So when you delete the endpoint, you can see that all the maximum paths, their length has now been reduced by 1 because we are uniformly deleting all the end vertices. So that all the paths in that tree, the length has now been uniformly deleted by 1. Okay, so basically when you find the eccentricity, you can see that eccentricity is the maximum path, and the maximum path occurs at an end vertex. So when you delete all the end vertices, what will happen? All the maximal paths, its length will uniformly be reduced by 1, or you can see that the eccentricities will uniformly be reduced by 1. So if I write down these eccentricities of a resultant graph, this will be the resultant graph. Okay, this is the resultant graph now when I deleted all the pen vertices, and the new eccentricities are written here, and you can see that the center is just the same. This point is just the same. The eccentricity has actually reduced by 1 here, only that is there. Apart from that, the center is exactly the same. So the new graph, so suppose the original graph was 3t, the new graph t dash which is obtained, that is also a tree, and the eccentricities would be exactly reduced by 1 for all the vertices, and the center is also just the same. Okay, so that is the idea. Even in this graph also, you can see that in this graph t dash also, you can see that basically the maximum eccentricities occurs when the other vertex is a pendant vertex. Okay, and again if I repeat this process, suppose I am deleting the pendant vertex again in this tree also, I will get a new tree in which the eccentricities of all the other vertices are reduced by exactly 1. Okay, and the center would just be the same. Okay, suppose here also I am going to delete all the end vertices. Okay, I am going to delete all the end vertices. What will happen? I will be getting a new graph, okay, in which the eccentricities of all other vertices are reduced by exactly 1, right, and the center would be exactly the same. Okay, again if I repeat this process again, it will end at some point. So sometimes I'll get a vertex like this, okay, or sometimes in some other cases I'll show an example, so I'll get an edge like this. Okay, so sometimes we'll be getting a vertex or an edge like this. Okay, this will get like this because this graph is finite, so at some point this procedure should end. Okay, so this graph is finite, so at some point you should this graph deletion of these vertices means you will be getting ultimately at some point a point or an edge. Okay, so when you get a point, you will have that point will be your single center, that point will be your single center, and if you get an edge, that those two edges will be your, those two vertices, those two end vertices will be your two centers. For example, if you look at, so this is in this example which you are dealt with, you are getting only a single center here. In this example, you are getting only a single center here. Okay, so if you look at some other examples, so let us look at some other example, some other trees, you will see that we will be getting, okay, for example, if you look at this tree here, okay, so here also we are going to apply all this all these procedures here. First you had a graph here, and you had all the, we have marked all the eccentricities in this graph here, and now we are going to delete all the vertices here. You can, what was the center in this graph? You can see the center, two centers are there. You can see that 4, and this is a center, and this is a center. Okay, now we delete all the end vertices. What will you get? You will be getting a new graph there, and the centers would be just be preserved as before, 3 3 there. Okay, again you delete all the n vertices, you will be getting this graph. Again the centers would be preserved here. Okay, finally when you delete all the n vertices, you will be getting this one. So you are getting an edge, so both of them will be the center. So in a tree, when you use these procedures, you have only two possibilities. Either you will get one vertex or you will get two vertex. So there will be one center or two centers in a tree. So that is the crux of the proof here. So I have actually illustrated the proof here. Now please go through the proof. After going through these illustrations, you will understand this. Okay, everything which you discussed earlier has become in the proof. So please go through the proof and try to understand by means of these illustrations, and please write down it, because they can usually ask this question also. It's a very simple question. A simple illustration will do. Okay, so please try to understand the proof by means of this illustration and try to write down the proof also. It's a very important thing. Okay, what is the proof here? What's the question here? Every tree has either one or two centers. Okay, so please go through the proof. Okay, and moving forward, now you have already proved that if a tree has two centers, there must be adjacent, because now you have already shown by means of this proof that you are getting this two centers as finally as an edge only. So basically, if there are two centers, both these centers would be adjacent. Okay, and similarly, the eccentricity of the center, okay, that is the minimum eccentricity, it is called the radius of the graph, the minimum eccentricity. So basically, the eccentricity of this graph, eccentricity of this graph eccentricity of center of this graph was actually 3. So the radius of this graph is 3. Okay, similarly, the radius of the other graph, so the radius of this graph, what is the radius of this graph? There are two centers are there. The radius is the eccentricity of the center, so it is actually 4 in this graph. Okay, so eccentricity of the center is called the radius of the graph. Okay, that is also there. They can ask you define radius of a tree. Radius of a tree. Okay, similarly, moving forward, the diameter of a tree is defined as the length of the longest path in T. Diameter of a tree is defined as the length of the longest path in T. Okay, and you know that in a tree can be only one path between two vertices. So basically, if you take the longest path in a tree, you can see that it will actually be the eccentricity of some vertex there. Like, is it clear? Why? Because in a tree there can only be one path between two vertices, so that longest path will actually be the only path between those two vertices. So it will actually be the eccentricity of those two vertices. So that I can see that the diameter we can also define as the maximum eccentricity also. Okay, so radius is the minimum eccentricity, diameter is also defined as the maximum eccentricity. Okay, for we can see some illustrations here. Two graphs are given here. So here the center is already marked in red here. Okay, center is marked in red here. So what is the radius of this graph? The radius of this graph is basically 2. And what is the diameter? Diameter is the maximum eccentricity, which is actually 4 there. Okay, and similarly in this graph the radius is actually 2. Okay, and what is the diameter? The diameter is actually 3 there. Okay, so we can see the diameter is not necessarily twice the radius, so radius is not necessarily half the diameter as in circle. It's a different concept there. Okay, so radius is the minimum eccentricity and diameter is the maximum eccentricity. So that's it. So these are some distance notions in the case of graphs. Okay, thank you.